and welcome to video 4 of my 6-part series on the AMC 10 tutorial videos. My name is Michael Liu and I'm from Agora Math Circle. In this video, we will be going over exponents and logarithms. First, I will cover the basics of exponents, then I will go over exponential identities. Afterwards, I'll go over solving exponential equations. And then after that, I'll start going over the basics of logarithms. And then I'll go over logarithmic identities, solving logarithmic equations, and finally I'll go over a couple of example AMC 10 problems. So just as a quick review in case you did not know this or you need a quick refresher, exponential expressions take the form of b to the x, where b is the base and x is the exponent. They can be read as b multiplied by itself x times. Normally, if you just say it out loud, you just say b to the x. So for example, 3 to the 5th would be equal to 3 multiply itself 5 times, which would be equal to 3 times 3 times 3 times 3 times 3. If you were to simplify this further, it would be equal to 243. Here are a list of exponential identities. So first we have b to the negative x is equal to 1 over b to the x. So this involves negative exponents. So for this, the use would mainly be if you had, say, some expression that values to 5 to the negative 2. Well, then you could use this identity to know that it's equal to 1 over 5 squared. So that's just what it is. And then you could evaluate further to get 1 over 25. So that's that identity. Next, we have b to the x times b to the y is equal to b to the x plus y. So an example for that would be, let's say you had 5 to the 3rd times 5 to the 2. That'd be equal to 5 to the 5th. And if you value that further, you would get 3,125. Next, we have b to the x divided by b to the y is equal to b to the x minus y. So an example of that would be 5 to the 3rd divided by 5 squared. That'd be equal to 5 to the 3 minus 2, which is equal to 5. So for these two identities here, if you just think about them, it's quite obvious to see why they work. If you had, say, 5 squared times 5 cubed, well, another way to write that would just be to say 5 times 5 times 5 times 5 times 5, and that'd be equal to 5 multiplied by itself 5 times, which is what 5 to the 5th is. So that's why that one works. And this one is just in reverse. So if you had 5 to the 3rd divided by 5 squared, that'd be equal to 5 times 5 times 5 divided by 5 times 5. So you can just cancel those out and you just get 5. So next up we have b to the 0 equals 1 when b is not equal to 0. So this is just any number or any variable taken to the 0 power, except for 0, is equal to 1. So if you see this, you know that would be equal to 1, assuming x is not equal to 0. If you see like 100 to the 0 power, well, that'd still be equal to 1. Now the exception is when the base is 0. There are some arguments about what the value should be when you take 0 to the 0th power. Some people say that it should be 1, some people say that it should be undefined, and you don't need to worry about it too much in the scope of the AMC contest because it'll almost certainly never appear. What you do need to remember is just that anything to the 0 power except for 0 is equal to 1. So next we have b to the 1st power is equal to b. Well, that's pretty self-explanatory because you're just taking one of that thing. So you can just ignore the 1. Next we have 1 to the x is equal to 1. That's also pretty self-explanatory because no matter how many times you multiply 1 by itself, it'll always still be 1. So next up we have a to the x times b to the x is equal to a times b to the x. Well, this just involves the distributive property. So since this is in parentheses, you have ab to the x. This is just in parentheses. It involves you distribute the exponents at each of these numbers. So you distribute that and that. Just remember that you distribute exponents. So next we have b to the x in parentheses to the y is equal to b to the x times y. Well, that's not too hard to see either, because if you have, say, x to the second power to the third power, well, you could first expand the inside to see x times x to the third power. Well, then you could see again that you're multiplying this by itself 3 times. Or actually, you don't even need to expand it that way. You can just see that you're multiplying x squared by itself 3 times. So it's x squared times x squared times x squared. Well, that'd be equal to x to the 2 times 3. So you can see why that works. Now notice, however, that this is different than if you had x to the 2 to the third power, because then you're taking exponents of the exponent. So this is not the same as this. If you were to value this, you would first take the exponent of the exponents, which would be equal to x to the 8, because that's what 2 to the third power is. And then, well, if you were to value this, that, as we saw earlier, that's x to the 6th. So that's something important to remember. So next we have b to the x divided by y is equal to y. It's equal to the yth roots of b to the x. So in case you didn't know, if you write this, it's just basically means to the yth root. So if you don't write it, it's implied that's the square root. So that would mean the square root. If you do write it, this means the cube root. So the square root of 4 is equal to 2. The cube root of 8 is equal to 3. So what this means is that the yth root of b to the x, that's just what this expression means. And it also is equal to the yth root of b taken to the x power. So this is pretty important to remember. So for example, we had b to the y 1/2. That'd just be equal to the square root of b. And remember that there's an implicit 2 there, but we don't write it since the square root is very common. And then if you say you had b to the 4/5, you could write that as the 5th root of b to the 4th. Or you could also write that as the 5th root of b to the 4th power. And that's just one of those properties of radicals. Because remember that if you can multiply the insides together, if you add b to the 5th root of b times the 5th root of b, you can multiply the insides together and you get the 5th root of b squared. So if there are any of these identities that you don't understand, you should go online and search it up and see why it is that, see how to use them and why it is that they work. Because these identities are very important for many problems. Although they don't tend to be tested as often on the AMC 10, however. I would also advise to look online to find even more identities that I did not cover here, because they could help a lot in the future with other math problems. Now I'll be going over solving exponential equations. When solving an exponential equation, the easiest method is often to manipulate the equation so that the bases of both sides are the same. So remember that if you had, say, 3 to the x is equal to 3 to the y. Well, we know for sure that x must be equal to y in order for the value to be the same. So that's just something to remember. So for example, if we had 3 equals 9 to the x, we know that 9 to the x is equal to 3 squared to the x. We can then use our identities to get 3 squared to the x is equal to 3 to the 2x. Now we have 3 is equal to 3 to the 2x. We can obviously see it that's 2x is equal to 1. Because there's an implicit exponent there, it's just 3 to the 1. But we don't write it because it's not necessary to say that everything is multiplied by itself one time because, well, everything doesn't matter if we write or not. So x is equal to 1/2. Now I will start covering logarithms. Logarithmic expressions take the form of log base b y, where b is the base of the logarithm. So they're basically the inverse operation to exponents. And a really important property for them is that if log base b to y is equal to x, then b to the x is equal to y. So just, if you can't remember, just remember that it kind of goes in a cycle. Like here, start from the base, go up, and go around. So b to the x is equal to y. So very important that if the base is not stated, such as log 100, it means that the base is 10. ln 100 is also a logarithm. In that case, the base is e. In case you did not know, e is the natural number. It's kind of like pi, where it has a defined value that never ends. I believe its value is around 2.7. So the base must always be greater than 0, and y must always be greater than 0. Also, the base cannot be equal to 1. So if you think about this, well, what logarithm is basically is that you find how many times the base is multiplied by itself to get y. So as you can see here, we have log 100. Well, the base is 10. How many times do we multiply the base by itself to get 100? Well, 10 squared is equal to 100. So then log 100 must be equal to 2. Another way you could have just found it is by changing it to this form. So if instead you said log 100 is equal to x, well, there's a 10 right there, so 10 to the x is equal to 100, and then x is equal to 2. So just remember that a logarithm is the number of times the base must be multiplied by itself to get this number right here. So in this case, 10 must be multiplied by itself 2 times to get 100. So the value of this logarithm is 2. So now looking back at this, well, why can't the base be 0, 1, or negative? Well, the base can't be 1 because for any number other than 1, it's impossible for 1 to, well, the only number that you can get from 1 multiplied by itself is 1. So if you had log base 1, 2, there's no value in which you could get 1. So if you had that equal to x, there's no value of x that you could possibly get to equal to 2. And then the base also can't be 0 for similar reasons, because if that was 0 instead, there's no value you could get it to equal to 2. And then y must also be greater than 0 because if you had log 2, but then you had a negative number, well, there's no value of x for the logarithm that could satisfy it. And then the base must also be greater than 0 because if you had log base of negative 2, and you said that's equal to x, well, there's once again no value of x that could satisfy the logarithm. So that's why there are those constraints on the values of that you can put into the logarithms. Sometimes they come in handy during question because it helps you to narrow down the possibilities in which you can solve an equation. Now we'll be going over some basic logarithmic identities. These identities are very important, and I'll be going over the proofs for 3 of them on the next slide. So first we have log base b of x plus log base b of y is equal to log base b of x times y. This is just kind of the inverse of the exponential identity. So remember, for exponents, if you have b to the x times b to the y is equal to b to the x plus y. It's just kind of the inverse, because instead you start off with addition instead of starting off with multiplication, and then you end with multiplication instead of addition. So an example of this would be if you had log 10 plus log 10, well, you know that's equal to log 10 times 10, right? That's equal to log 100, which is equal to 2, because remember, if the base isn't stated, the base is 10. We can also verify this because log 10 is 1, log 10 is also 1, and we get 2. So next we have log base b of x minus log base b of y is equal to log base b of x over y. So this is once again the inverse to the division exponential identity. So for example, if we had log 100 minus log 10, well then that would be equal to log 100 over 10, which is equal to log 10, which is equal to 1. Well, we can also just evaluate this straight off. Well, log 100, we know that's 2. Log 10, that's 1, and we still get 1. So again, I'll be going over proofs for some of these in the next slide. So now we have log base b of x is equal to log base c of x over log base c of b. And this works for any real number c greater than 0. And the reason why this is, remember that there are constrictions on what the base of a logarithm can be. So also c cannot be equal to 1, because it has the same restrictions as the base of any other logarithm does. And this is often referred to as change of base. So an example of that would be, let's say we had log base, I don't know, let's say log base 100 of 10,000. Well, if we use change of base, we can change the base. So let's have c equal to 10. Well, then we can have log 10,000 over log 100. Well, that'd be equal to 4 over 2, which is equal to 2. And we can also verify this straight off. How many times does 100 need to be multiplied by itself to get 10,000? Well, it needs to be multiplied by itself twice. So you can see that right off the bat that it's equal to 2. Normally you wouldn't use it in these situations since it's so easy to evaluate the logarithm straight off, but it's much more useful for more complicated problems when you need to simplify more expressions. So next we have log base b of x to the a is equal to a times log base b of x. So an example of that would be if we had log 10 squared, well, we see that we could just move the 2 over here, and then log 10, and that just be equal to 2 times 1, which is equal to 2. And you can also evaluate it straight off, because that's equal to log 100 which is equal to 2. And next, down here we have b to the log base b of x is equal to x. So for here, if for example we had 10 to the log 5, that would just be equal to 5. And then now we have x to the log base b of y is equal to y to the log base b of x. Well, let's say we just had 2 to the log of 2 to the log 10, that'd be equal to 10 to the log 2. So now I'll be going over 3 examples of proofs for the identities. The 3 identities I'll be using will be log base b of x plus log base b of y is equal to log base b of x times y. Log base b of x is equal to log base c of x divided by log base c of b. And b to the log base b of x is equal to x. So the first one, we say let log b of x be equal to m. And then let log b of y be equal to n. So then we know that x is equal to b to the m and y is equal to b to the n. Because remember, we can do the thing around. B to the m is equal to x. And then we could just do the same thing with this. B to the n is equal to y. So then we have x times y is equal to b to the m plus n, because we're using our exponential identities. So log base b of x times y is equal to m plus n, and we know this because, and well, that's just because there's a step in between where we could replace xy with b to the m plus n. And then we know that we could just move m plus n over. So then we get m plus n log base b, and that's log base b of b, and that's just 1, so that's just m plus n. And then we can replace m plus n with log base b x plus y. So there we have it. Log base b of x times y is equal to log base b of x plus log base b of y. So for our second proof, we have log base b of x is equal to log base c of x divided by log base c of b, the change of base. So for this, we once again set the values to dummy variables. Log base c of x equals m, log base c of b equals to n. And then we once again have this setup, similarly to what we have here. So now we have log base b of x is equal to log base b to the c to the m, because as we can see here, we have x is equal to c to the m. And then using our other identity earlier, we can move m over, so that's m times log base b of c is equal to log base c of x times log base b of c, because we set this equal to m. So you can plug it back in. And then that's equal to log base c of x divided by log base c of b. So just a quick note that log base b of c is equal to 1 divided by log base c of b. I won't get into why that is, but if you just want to make sure, this is nowhere near concrete proof, but just as an example, if you have log, let's say 10 of 100, that's equal to 2. Well, if you switch the 2, we have log 100 of 10. Well, that's equal to 1/2, because the square root of 100 is equal to 10. So we can see here that this holds true, at least for these values. So now we have our last proof. B to the log base b of x is equal to x. So once again, we set it equal to k, another variable. So that we take a logarithm of both sides. So we take log base b of b, and then we also take log base b of k. Well, after we do that, well, then we modify the left side of the equation. Log base b of b to the log base b of x. Well, using our identities, we can move the exponents down. So then we have our exponent, log base b of x, times log base b of b. Well, log base b of b is just 1 because, well, there are a couple more identities I didn't mention, but basically they are log base b of b equals 1. That's pretty self-explanatory because any number will go into itself one time, except for 1 and 0, but that's beside the point because you can't have a base of 1 or 0 anyways. And then the other one is log base b of 1 is equal to 0. Well, remember that you can just do the flip around thing to convert to an exponential expression, and we have b to the 0 equals 1. And that's always true except for when b is 0, but the base can't be 0, so that always holds true. So we know that log base b of b is equal to 1, and so then this expression would be equal to log base b of x, which is equal to log base b of k, because, well, that's just the right side of this equation. So then we get k equals x because, well, everything else in the equation is the same except for x and k, so they must also be the same in order for the equations to be equal. And then x is equal to, k is equal to b to the log base b of x. So we've proven that b to the log base b of x is equal to x. So note that the techniques using these proofs are often useful for solving exponential and logarithmic problems. If you do not understand the way in which I went over the proofs, I would highly recommend you to look at some other person going over the proofs. And if you did understand, well, maybe try to prove some other identities yourself, because the experience could be very helpful. I'll be covering solving logarithmic equations. Similarly to exponential equations, manipulating the equations so that the bases of the logarithms are the same is generally the first step to solving logarithmic equations. The change of base identity comes in very handy for solving these equations. So for example, if you had log of x, well, equal to log base 5 of 40, well, remember, we have to try to change the base so it's the same. So I decided to change the base on the right side because usually it's easier if you try to keep the base of 10 or a base of e depending on what kind of problem you have. That's generally easiest. So I changed the base to 10. So log x is equal to log base 10 of 40 divided by log base 10 of 5 using the change of base identity. And then just using the loop over thing, because you remember there's a 10 here, we can have 10 to the power of this equal to x. So then we've solved that. X is equal to 10 to the log 40 divided by log 5. You could evaluate that further with a calculator, but I will not be doing that. So we have an example problem from the 2020 AMC 10A. This is problem 1. It's a fairly short and simple one. What is the value of that expression? If you want to solve it yourself, you can pause the video right now. Otherwise, I'll reveal the answer right now. So this is a simple problem as long as you remember that any number raised to 0 power is equal to 1. So we can simplify the expression to 1 plus 1, which equals 2. In case you want to do it the long way, well, you can see first here that we have 1 to the 9th. 1 to the 9th is just 1, 0 to the 1 is just 0, and then 2 to the 0 is just 1. So that's what we get in the end. Although you could also just see that there's a 0 here, which means that the whole thing will evaluate to 0 because 0 is what the exponent that's last. And then over here, well, first off, this evaluates to 1, and then you're taking 1 to the 1 first power, that's just 1 again, and 1 to the 9th power, that's just still 1. So then you get 1, 1 plus 1, that's 2, C. So you could do the whole process just to be sure, or you could just see that it's 2, and then right above it is 0, and then that must be 1. That's not a good 0. You could just see that it's 2 and a 0. I mean, even with the parentheses over here, you can still tell that in the end it's going to be a 0, because no matter what the top of here evaluates to, you'll still have 0 to some power, which will always be equal to 0. Unless that power evaluates to 0, but that won't happen in these multiple choice questions. Unless one of the choices is the correct answer is not listed, which I have not seen. So now we have a slightly more difficult problem. This comes on the AMC 12A because logarithms don't show up as often on the 10A compared to the 12A in other competitions like the AIME. So this is problem 10 from the 2020 AMC 12A, and it reads, there's a unique positive integer n such that log base 2 of log base 16n is equal to log base 4 of log base 4 of n. What is the sum of the digits of n? If you want to try to solve this yourself, you can pause the video and try it. Otherwise, I'll go over the answer right now. So I will be going over 3 different solutions to solve this problem. So this solution mainly involves using change of base and logarithmic identities. So first we have our original equation up here. Well, next we use change of base on the right hand side of the equation. Well, this gets us, well, we decide to change the base to 2 because that's what the base is here. So using change of base there, well, if we had form log base b of y would be log base 4 of n, so log 2, log 4n, and then b is 4, so log 2 of 4. And then we can simplify that further because log 2 of 4 is equal to 2. So then we just multiply both sides of the equation by 2, and this is what we get. So then remember that this identity also works in reverse. You can move the coefficient here up as an exponent. And now we have log base 2, an expression, and log base 2 of another expression. Well, you can just remove the log base 2 because clearly the expressions inside must be equal to each other. So then this is what we get. Well, now we can use change of base again on the inside of this. So then we get log base 4 of n is equal to log base 4 of 16. We choose a base of 4 because that's what we have on this side over here. Well, we know log base 4 of 16 is 2. So then remember that we distribute the exponents. So really, you could write this as this expression here. It could also be written as log base 4 of n squared equals log base 4 of 16 squared, because you can distribute the exponent. So that's how we get here, because we can cancel one of these with that. So we divide both sides by log base 4 of n, then that's 1, and then we just have log base 4 there on top, and that's equal to 1. Well, you multiply both sides by 2 squared, so log base 4 of n is equal to 4. So then we can just do the thing around. 4 to the 4th power is equal to n, which is what we have here, and n must be equal to 256. Well, the sum of the digits would be 2 plus 5 plus 6, which is equal to 13. Next, we have a solution using exponential expressions. So first we have our base problem here. Well, since we know these are equal, we set them both equal to x. Well, then we can easily convert both of these into exponential expressions, because 2 to the x equals log base 16 of n, 4 to the x equals log base 4 of n. Well, after that, we see that n equals 16 to the 2 to the x, because we just do the same thing again. 16 to the 2 to the x is equal to n. It's right here. And then 4 to the 4 to the x is equal to n. Then we get that both of these are equal. Well, then we know that 16 is equal to 4 squared. And then this is still to the 2x. So we can just use the identity to see that it's 2 times 2 to the x, which is equal to 4 to the 2 to the 2x. Because we can just once again see that 4, that's equal to 2 squared to the x, right? Well, using the identity, that's equal to 2 to the 2x. So that's how we got 2 to the 2x there. Well, in between, there's a step. Well, we know that 4 to the 2 to the x plus 1. And the reason why we know that this is equal to this expression over here is because, well, 2 to the x is 2 multiplied by itself x times, and then this is just 1. So using the identity we showed earlier, we can just add the exponents together. And that's equal to 4 to the 2 to the 2x. So that's how I know that x plus 1, or 1 plus x, it doesn't matter, is equal to 2x. So then manipulate, subtract x from both sides, and we get x equals 1. So remember that, since both sides of this have 4 squared, and then another exponent, these must be equal to each other. So then we get n is equal to 16 squared to the first power. We just plug x into here. That's equal to 256. And the sum of the digits is 13. So finally, we have solution 3, which involves educated guessing and checking. So that's our original equation that we have to solve. Well, we can see that n is most likely some power of 16, because it's an integer, and, well, it must fit this equation. And we can see that there's log base 16. In all probability, n must be some value of 16, some power of 16, in order for both sides of these to equal each other, as it's more likely if they're all round numbers. So first, we test n equals 16. Well, we plug in n, we evaluate, and then ultimately see that this is equal to 0, while the right side is equal to 1/2, so n is not equal to 16. Well, next we test n equals 256, which is just 16 squared. So we plug it in, we evaluate, and then we end up seeing that both sides of the equation are equal if n equals 256. So based on this, we have verified that the value of n is indeed 256, and the sum is 13. This method would be the fastest if you found it out, but it will not necessarily always work. And sometimes it would actually end up being the slowest. If, for a different problem, if n instead was equal to 16 to the 10th power, because it'd take you a long time to test all of the values up to 16 to the 10th power. And for other problems, you just simply can't guess, and you just have to figure it out by yourself. So this concludes the 4th video of my 6-part series on an AMC 10 tutorial. I hope you have enjoyed this. I hope you've enjoyed listening to this. If you didn't understand my solutions for the last problem, I encourage you to check the Art of Problem Solving website to look at more solutions and different ways of explaining them. Thank you for watching.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the